All right, we've got two topics in this pre-lecture, and we're hopefully going to not take that long on these because you've seen them before, but as a quick review, we're going to talk about force and weight. So I'm not going to explicitly define force and weight as I go through problems in every lecture that we have, so I just want to make sure that we hit these concepts first because I'm sure that you've seen them before, but it always helps to have a quick handy review. So force we define as the product of a mass and an acceleration. So this is Newton's second law, which you have hopefully seen in your physics classes, and basically what it says is that the sum of the forces is equal to a mass times an acceleration. Normally we see force in units of newtons, and as we defined in our units pre-lecture, a newton is equal to a kilogram times a meter per second squared. Now you may see other units of force. It is 100% possible, especially if you are a civil engineering major and maybe you're going into structures. You might see a unit called a dyne, and a dyne is 1 gram times a centimeter per second squared. And because we are working in the United States, and at least in this class and possibly in your jobs, a pound force is also a possibility for a unit, and that is equal to 32.174 pound mass times a foot per second squared. So these are the units that you can see for force. So as an example, what force is used to accelerate a 4 kilogram mass at 9 meters per second squared? Well, we simply multiply those two numbers together because they are a mass and an acceleration, and that gives us force. So if we multiply together, we're going to get 36 kilograms times meters per second squared, and we know that that unit, that compound derived unit, is equal to a newton. So pretty straightforward, at least for the purposes of this class. We also will sometimes see weight, especially when we do energy balances towards the end of class. And remember that weight is just a special example of Newton's second law where we're talking about gravitational forces. So acceleration is acceleration due to gravity. So weight is equal to mass times the gravitational constant, which is g, and we define g as 9.81 meters per second squared or 32.2 feet per second squared. And remember that your weight does not change much with your position on Earth because gravity is a constant. So that's it in terms of force and weight. We just want to make sure that we have those concepts defined as we go forward in class. The other concept that we want to talk about here is what we call dimensional homogeneity. So you've probably actually seen this, you just probably haven't seen these specific words. Homogeneity means everything's the same. So effectively what dimensional homogeneity means is that all terms that get added up together on one side of an equation have to have the same units as the other side, everything that's on the other side. So basically everything has to be in the same units when you have an equal sign. So what's on one side of the equal sign has to have the same units as what's on the other side of the equal sign. So as an example, let's consider this equation that's up on the slide. We have d in units of feet is equal to 3 times t, and t is in units of seconds, plus 4. Now, in order for this equation to be true, we need units on the constant 3, and we need units on the constant 4. So if d is in feet, that means that 3 times t must be in feet, and whatever 4 is by itself also needs to be something similar to feet, right? So if this equation is valid, we want to know what are the dimensions of 3 and 4 if we have consistent units. So remember, when we talk about dimensions, we're talking about length, time, mass, that type of thing. And units are the actual things like feet, seconds, hours. So take a second to pause this video, answer this question for yourself, and I'll show you the solutions on the next slide. All right, hopefully you pause that video because it's important for you to learn this yourself. So if we're looking at dimensions-wise, it's actually probably easier to answer the second question. If t is in seconds, and we know that 3 times t has to be a foot, we know then that 3 has to be in terms of feet per second, because that way seconds are going to cancel and we're going to get feet. And I kind of give you the answer to what are the units for 4, and those are feet, because anything that gets added together, 3t plus 4, 3t has to be feet and so does 4 in order to be able to add things up. So if we're going to backtrack that to what dimensions we have, then we know that 4 has to have a dimension of length, right? Foot is a dimension of length. And then the constant 3 must have a dimension of length per unit time. So just a very kind of formalized way of saying things that you already really know about units, but this is what this concept is all about. So let's try another example really quick to make sure that this is very clear moving forward. If we have a quantity K that depends on temperature using this following equation, we want to know what the units of the 20,000 are. You know the units of the quantity 20,000s are calories per mole, and T is in terms of Kelvin. We want to know what the units of the 1.2 times 10 to the 5th and the 1.987 are in order to be what we call dimensionally homogeneous. So take a pause, see if you can figure out what the units are of those two numbers, and then we'll see the solution on the next slide. Did you take the pause? I hope you are. I hope it helps you. So as a solution, right, we want to make sure that all of the units basically cancel out in this specific equation. So that EXP, remember, is the E operator. It's the inverse of the natural log, and that is dimensionless. It's a number. It's an irrational number. So if we take a look at this, the answer is going to be that 1.2 times 10 to the 5th is going to be moles per centimeter cubed times seconds, and that 1.987 is going to be in units of calories per mole times Kelvin. Now, this might not seem like a very important concept right now, but once we get into things like pressure and temperature and isotherms, we're going to have the ideal gas constant. And the ideal gas constant has lots of different units, and using the correct constants in the correct units is going to be very important. So think of dimensional homogeneity as another potential way for you to help check yourself when it comes to units when you're applying equations, because that's a very common mistake that people make. It's not that you don't understand how to solve a problem, it's that perhaps you forgot the units. So this is another great way for you to check yourself as you're going through your equations. That's going to finish us off for this pre-lecture. We've got one more pre-lecture in Chapter 2, and that'll get us through all of our review before we start the rest of the information in this class.